All right, folks, good afternoon. And welcome to the July ASQ Lean Enterprise Division webinar. My name is Manny Veloso. I'm going to be one of the hosts today, and Ellen Erner is going to be joining us shortly. Today's webinar is Predictive Quality with Industrial AI for Zero Defects Manufacturing, presented by a gentleman that I've had an opportunity to speak with quite a bit over the last few months. His name's Mo Abali. I think you're going to enjoy this webinar quite a bit. Our next webinar is Wednesday, February 10th. It's going to be Lance Coleman, which is a name that many of you may know, and successfully implementing Lean in a COVID-19 world. Just a little bit of housekeeping here, folks. So you can expect shortly after the webinar ends to get your RU certificate of attendance. If you did not, then please let me know. I'm going to put my email address into the chat just in case if there's any issues or if you have any questions after the fact. If you're looking to get a copy of the presentation itself, the presentation deck, you should communicate with Mo Abwali directly, and I'm sure he'll have his contact information as part of the presentation. Now, if you want to ask a question, you can do that. Certainly, if you go to what I think of as the GoToWebinar control panel, you can take a look and you'll see questions, and then I'll be monitoring that, and we'll take questions at the end of the presentation. We expect that Mo's going to speak for about 40 to 45 minutes, which gives us 15 or 20 minutes for questions. Okay, having said that, I'm not going to read this introduction out to you, but Mo Abali is the CEO and managing partner at IoTCO, the Internet of Things company, and I'm going to let him introduce the rest of his background and let him take over from there. Okay, so I am going to turn it over to you, Mo. Welcome, and thank you for being here today.
Thank you for the opportunity, Manny. Just want to confirm you hear me well, you see my slide?
Absolutely, yes, you're doing well. 5 by 5, as they say.
All right. Yeah, thank you for the opportunity to give this presentation here to the ASQ chapter. My name is Mo Abwali. I've been in the industry for about 22 years, and I come from an automotive background, actually, and have been doing IoT, Industry 4.0, predictive maintenance, predictive quality in automotive settings and in other manufacturers. So today, my topic is the use of industrial artificial intelligence and predictive quality specifically for zero defect manufacturing. Only one slide just to introduce who we are and why I'm here. I used to work at Toyota in my younger days, and at Toyota I was actually a maintenance engineer, and I interface also with the quality department. So at Toyota I had the pleasure of supporting the TPS pillar on maintenance and quality improvements. We focus as an organization on smart factory applications, and quality is a big area where we play in addition to maintenance. And we in a nutshell are focused on the digital and industrial transformation of manufacturers. Okay, we provide consulting and training, similar to the session I'm doing here today. A lot of the content I'm going to show you is a part of our IoT Academy, which provides training. And we work in the data science and predictive analytics area. And I'm going to talk today about predictive quality, which is focused within PDX. And then we also do other work in the Internet of Things domain. So our DNA is manufacturing, and our passion every day is to support manufacturers on their journey towards what we call a zero downtime, zero defect mode of operation. So I'm here today to talk about three things. And as Manny mentioned, at any time, please write your questions in the Q&A, and I'll do what I can to tackle every question at the end of the presentation. So I always like to start with the business case, right? It's important to understand the business side of things, and then to start talking about technology. Business drives technology adoption. So I'm going to kind of paint the picture of what is the business case for predictive quality and predictive analytics. I'm going to talk about the technology. I'm gonna have a case study driven presentation. I want to share with you some things that are happening in the CPG space, consumer product goods, automotive primarily, and I have some ideas at the end of the presentation on how you could tackle predictive quality and in general quality 4.0. Okay, so let's start with the business case. It's all about productivity improvements. Okay, at the end of the day, it is important to understand what is your why as a business. What is the why? Why are you doing this? Okay, you know, I want to improve quality. Well, that's great. Okay, but how do you measure success, right? So within manufacturing, a key metric is overall equipment effectiveness, which is your availability, performance, and quality. You know, a lot of you may have heard of this metric. I'm going to focus today more on the quality side of it, but you know, improving uptime and improving performance is also key to the operation. Using predictive analytics within a smart factory is usually geared towards uptime improvements, improving spare parts, improving maintenance and labor scheduling activities, right? But our focus today will be more on the detection and reduction of waste, of scrap in the manufacturing sector. So the concept of quality 4.0 or predictive quality is the key concept that we're going to be discussing today. This is an example of, you know, a survey, actually, survey results of some of the manufacturing clients that we work with, and the average improvements that they have been able to witness by implementing Industry 4.0 and Smart Factory within their operations, right? By using tools like process monitoring and artificial intelligence, you know, our manufacturing clients were able to reduce scrap by, you know, a fractional 1% up to 5% by implementing the right tools, right, and empowering their people to use those tools. At the end of the day, it's about people, process, technology, right? It's a three-legged stool, and it is not just about the success of technology, but it's also about the success of the people and implementing the right process in your operation to drive the results. So driving zero downtime and a zero waste manufacturing mindset requires us to always think of the why and to understand the business case. And once the business case is well understood, we're able to start going deeper into the technology and the how of how we can make it happen. I want to start with two small use cases, okay? Both are automotive clients actually, but they have completely different business cases. The first business case is geared towards uptime improvements, right? So this automotive manufacturer, they have multiple plants. You know, they have issues with machinery going down. They're a very high volume operation. You know, their machines are fairly old, legacy machines on the factory floor. So capturing data was always very difficult. And it was very difficult to find spare parts for those machines because they're fairly old, right? So by using real-time connectivity, sensorizing the line, and capturing data using industrial artificial intelligence and advanced analytics, they were actually able to receive an AI Leadership Award in 2019 from the National Association of Manufacturers by implementing AI in an accelerated way to support their manufacturing operation and to get an ROI within about 3 to 6 months. But the use case that I'm going to come back to at the end of this presentation, actually, to conclude the presentation, is focusing on predictive quality of high pressure die casting. It's a very unique industry, actually. Did you know that the scrap rates, the industry standard, industry norm scrap rates within casting is somewhere between 9 to 15%, okay? So just imagine you're scrapping 9 to 15% of your parts, and it's considered industry normal. You're doing great, you know. So by using industrial AI and the case study that I'll show you at the end of today's presentation, and correlating the machine parameters, there's about 40 to 50 casting parameters every shot, every 6 seconds, and correlating them to the quality output. Am I going to make a good part? Am I going to make a scrap? Okay. And doing this every 6 seconds for every shot of aluminum cast going to the machine, right, can be significant ROI for the business. We actually call this project the power of 1%, because a fractional 1% reduction in scrap in a casting plant, a mid-sized casting plant, which is about 25 to 40 machines, is around a $250,000 in savings per plant per year. Okay, that usually exceeds 100% ROI for all the the software and the infrastructure that you need to put in place to make that happen. But predictive quality is critical to the businesses today. Okay, there are some gaps, there are some barriers that we're going to talk about to make this example here happen. But it is a mission critical application that allows for the use of advanced analytics, collecting data every cycle of the machine and correlating it to quality and making prescriptive decisions, right? We need to prescribe to the machine every 6 seconds and tell the machine, are you making a good part or are you making a bad part? We call that auto part segregation actually on the machine. So there's no need for human involvement, the machine automatically learns and understands if it's making a good part or a bad part and is actually scrapping the part automatically. Bokar actually received the 2020 AI Leadership Award from National Association of Manufacturers last year, and I'll be shortly presenting that case study today. So what is Quality 4.0? Let's start from the fundamentals, right? There's a lot of definitions out there. I like a very simple definition actually, and the definition is really the application of the fourth industrial revolution, digital tools, okay, to quality management within the value chain. Quality 4.0 is not just about manufacturing. I mean, my presentation today is focused on manufacturing, but Quality 4.0 has many applications across the whole value chain, okay? This is a great study, actually. I can share that with you, but you can Google it online. It's BCG's survey, which was conducted in collaboration with ASQ. And it's showing the top use cases selected by survey participants in the factory floor. Predictive quality being one of those use cases, but other use cases include the use of machine vision and the use of digital work instructions on the factory floor. So I'm going to focus more here in the green tile, but keep in mind there's so much more, and I'm sure some of the webinars and presentations you guys are going to attend this year are going to focus on other areas of the value chain. So great publication, but it's also important, as with any other strategy, that we create a clear vision and a clear roadmap of what does Quality 4.0 mean to your business and the people, process, technology component to ensure success with Quality 4.0. Great publication, BCG ASQ. A simpler definition, which is going to be the focus of my presentation today, is a predictive quality or a PDQ solution detects and diagnoses and predicts deviations in critical process parameters of machinery, like casting, in order to detect, diagnose, and predict that the quality of the actual final product that is being produced, okay? Whether it's an aluminum cast, whether it's an injection molded part, whether it's a CNC machine part, right? So how do we detect, diagnose, and predict quality issues, which obviously are driving improvements in some of the pain points that are related to quality? Cost of scraps are high, okay? Cost of reworking that scrap and the time it takes is also high if you're able to rework it. Decreased productivity and efficiency, increased time to actually inspect the parts, and that leads to loss of time and loss of profits, okay? Just imagine you're making a part every 6 seconds and you have to go and inspect every part, that's extremely expensive in terms of time and effort for the business. Warranty claims. I'm going to show an example at the end where, the cost of that part as it goes down the value chain from casting to machining to painting, and then it goes to the end user, it's exponentially increasing. And if a bad part goes to the end user, the cost there is priceless. You cannot put a price sticker on that, because warranty claims and recalls are going to kick in, and then it becomes significant loss for the business and potentially reputation issues. So how can we use predictive quality techniques to catch quality issues right at the source, right at the casting machine, right at the CNC machine, right at the molding machine, depending on what is critical for your business, right? So keeping this definition in mind, our goal here is to really create a multivariate model, right? There's a lot of inputs going in that could affect the quality of the part. There are process parameters. There are material properties and characteristics that have an impact. There are product specifications, inspection, right? And quality information. We need historical data, right, about inspections to be able to build and train these AI models. Not to mention expert domain knowledge, right, needs to be leveraged into those models to ensure the accuracy of the predictions, all right? So I like this definition here, you know, because all these areas, all these inputs need to be leveraged in the configuration and development of a predictive quality solution in order to be able to support the ROI areas and use cases that we discussed about, shown here. And sometimes it's not easy to capture all those data, right? It's not easy to synchronize all that data and bring them together in one place in a synchronized fashion so you can actually run these models. That's one of the bigger gaps. But before talking about gaps, you know, the application I'm going to show today is automotive centric and consumer product goods. But many applications are out there, right? So think about your business in the electronics and the semiconductor industry, you know, making chips, right? We had projects where, you know, if you think 40 data parameters in a casting machine every 6 seconds is a big number. In the semiconductor industry, there's about 1,000 chemical-based process parameters, 1,000 variables that are collected in milliseconds in some cases that need to be analyzed very quickly, which would indicate the quality of the wafer, the semiconductor chips that are being produced in a fab, right, in a fabrication area. So it becomes a big data project, and ingesting that data, working with that data, converting that data into actionable information is not an easy task. It requires analytical solutions that are implemented in a systematic way to improve quality for those, in some cases, heavily regulated manufacturing sectors like semiconductor and food and bev. So what do we need to make this happen, right? And I'll show you the case studies, but I think this is a great summary of all the case studies. You know, we need inputs, right? We need historic product quality data. I mean, to model and create any AI type of template, historical data is required. And, you know, in unfortunate cases, this may not be available. So we would have to implement a system and collect that historic data, right, in a synchronized fashion. Expert domain knowledge is always key initially to understand the different product IDs that are running on the machine. Every product ID has different thresholds, different material characteristics, and so on and so forth. That needs to become part of the data map or the data model that I'm injecting into my my AI, my analytics. And availability of key signals, right? So we can do this offline, but how can I implement this online? You know, how can I implement this with direct integration to the PLC on my machine, on my line, and an image camera that's on the cell, and being able to handshake the machine data and the quality data, right? So the connectivity, the infrastructure is a key, you know, area that needs to be prepared for us to be able to run these solutions online. So what is the output? I mean, obviously we're predicting part quality, right? Green, yellow, red. Is this going to be a good part predicted? Is this going to be a bad part? But in some cases there are suspects, right? You know, we call them yellows. You know, to be conservative, to be cautious, you know, those greens and yellows are rejected, you know, and are inspected. Or sorry, the yellows and reds, you know, the suspects and the rejects are rejected, and the green can pass, right? So that's predictive part quality. And of course, what is required to empower the shop floor personnel and the quality people to access that data? You know, these dashboards are mission critical because we're talking about making real-time decisions on part quality on the shop floor. And warnings and alarm thresholds are also key. You know, the sensitivity of those thresholds to reduce, you know, false alarms and false positives and things of that sort need to be properly validated and to ensure the prediction accuracies are high, right? So these are the types of events that usually happen that lead to quality issues in a typical manufacturing environment. I mean, process parameters, like in the casting or molding application that I briefly mentioned. I mean, a drift on those parameters can lead to issues. And I mean, mind you, clients today are using SPC products, right? Statistical process control. But in many cases, those SPC solutions are looking at a single variable at a time. And the use of predictive quality enables us to use AI and to use a multivariate approach that looks at all the parameters being collected, 40 parameters, 1,000 parameters, and making correlations. And SPC is usually not geared towards that. So predictive quality is a natural extension of using SPC on the factory floor. So with this short introduction, on some thoughts around what is Quality 4.0 and what is predictive quality, I'd like to browse through some case studies and then give you a short kind of motivating conclusion at the end. Let's start here, okay? Regardless of how you do it, the architecture is always a three-piece architecture. There is a data lake, there is industrial AI application, and then there are use cases that are delivering the user experience and the decisions to the end user, right? So we're talking about what is the relevant synchronized data for predictive quality. We're talking about asset-related data coming from the machine control. We're talking about process parameters like the temperatures and the pressures and the critical variables that indicate quality. We're talking about quality characteristics. Some of them come from the machine. Some of them may need add-on sensors like image data, for example, or even video data in some applications. And then we're talking about, ingesting that data, synchronizing it, making sure it's labeled in a proper way for the application, and then starting to correlate the machine data with the quality parameters and delivering use cases for the client. So when it comes to predictive quality, we're talking about two key metrics here. We're talking about part health, green, yellow, red, good part, suspect part, reject part, okay? So just imagine converting all that data into a decision on part health, okay? And the process behind it that I'm gonna show. And then defect prediction and diagnosis, actually, missing word here. What is the root cause, right? Why is this a suspect part? Why is this a reject part? Is it my temperature signal? Is it my pressure signal? Is it which variables or which part of the process is impacting the quality issues on my machine, right? So now if we take this and we look at the actual process that makes it happen, it is important to follow a systematic process, right? So the process starts with data collection. It goes into preparing that data, ingesting it, processing it, making sure the data is usable, right? Some data is noisy, some data requires outlier removals, filtration, and other techniques. And then feature engineering, extracting metrics, statistical metrics from the raw data that are meaningful, that are highly correlated between the process and the quality, the machine and the quality, right? That's the handshake that we have here. And then training an AI model that allows us to assess the health of the part. What is green, what is yellow, what is red mean? What is part health, right? And some of the applications we do are data-driven applications. They are multivariate. The 40 parameters, 100 parameters come into the system. Meaningful, highly correlated features are extracted. And then we're able to create a model based on this. So it's like a fingerprint. This is a fingerprint of a good part. This is a fingerprint or a signature of a part scrap. And it could be scrap type A, type B, type C, type D. You got different types of scrap modes that occur in the manufacturing operation, right? So once you have, that labeled data, that correlated data, the solution learns, actually. It learns those signatures, and that's your training. That's the training of the AI model. And then you're able to start doing predictions. Of course, every prediction comes with a caveat, which is the accuracy of the prediction, right? We need to work towards a high confidence interval of prediction, usually beyond 95%, because you don't want to start, letting good parts be rejected or letting reject parts be accepted, right? False positives, false negatives. So, there is an amount of training data required to get these systems working for each type of scrap that happens on the factory floor. And usually we need about 4 weeks of baseline data, okay, for each part ID. So I'm not talking about years of data. I'm talking usually about 4 weeks of each type of baseline. And then diagnosis, right? What is the root cause? And I'll show you some examples of how we're finding the root cause, which parameters, which signals are actually leading to the quality issue. So the challenge here is, when you go into manufacturing, it is not just about robots, right? It's about, I have robotics, I have CNCs, I have casting and welding and molding, I have stamping, right? Different parts, different processes. So the systematic approach still stands, it's still the same, but there is a series of templates that need to be created, right? Each one of these assets has a different behavior, different type of parts, has a different data map, right? There are specific parameters that indicate quality of a spot weld on a robot or a laser weld on a robot, right? There are specific parameters that indicate casting issues, or my CNC machine has a tool. My tool is creating the surface texture, surface roughness of my part, right? So if there's a degradation in my tool or spindle, I'm going to start having a part with a bad surface roughness in a precision industry like aerospace. So many examples. So my message here is, it's important to apply the systematic process in different ways to allow the user to understand the specific data map and to have that analytics workflow that I showed, from signal to feature to part health, part prediction, and part diagnosis, in a systematic way, okay? And these things have been well studied over the years. I'm not telling you this is a new field, right? This field has been around for many years, decades actually. But now with the faster computational speeds and the ability to implement the solutions online versus offline, it is actually speeding the implementation timeframe significantly on the factory floor. So some of the challenges are usually around the infrastructure and the connectivity and client type of responsibilities, but those challenges can be mitigated. So I'm going to browse through some case studies, okay? And I'm going to start with a case study from a CPG manufacturer. This CPG manufacturer, started to have some issues with warranty claims on their ovens, okay? They make ovens. Maybe you have their ovens in your houses, and also dishwashers, okay? And clients were calling and saying, hey, when my dishwasher heats, it's cleaning my dishes, over time, my door starts to crack, okay? So just imagine you're running your dishwasher and, a few months later, cracks happen on the dishwasher due to the heat and the material fatigue, right? Not a good problem to have. Phone call, service, warranty issues, recalls, right? So we went in this application and we looked at the process, and the process had a steel coil, there's a forming station and a line, and then there are finished ribs like the one you see here, right? And then there is a defined data map. We need data from the coils, data from the forming stations, and then quality data regarding the finished ribs. And we want to implement an online system for predictive quality that is predicting with the highest level of accuracy right on the manufacturing floor whether you're going to make an oven with a cracked door or whether this oven is okay to ship to the customer, okay? So to make this happen, there's a data map, right? Remember my picture? There's a data map, there's analytics, and then there's a deliverable, right? So I need to understand the material properties of that steel, going into my line, okay? Number one, because different material properties exhibit different, behaviors on the manufacturing floor. I need data from my forming station. I need the operational parameters and I need specific sensor readings, right? And then that data needs to be correlated with the final product check. So there's a history of the final product check, and there's a history of some of the warranty recalls that occurred, the serial numbers that were back traced. So, let me summarize it by saying there's a traceability system, right? And traceability is very important when it comes to predictive quality. you need to be able to serialize your parts or with a QR or a label, and that part in a manufacturing setting is usually traced. So there's an electronic trace record that tells you every operation, process parameter, person. It's like a birth record of the part, birth certificate of the part. So now when the predictive quality template is implemented, it's looking at the target quality, right? And it's making predictions on recommended operation settings of the line that allows me to maximize quality and to reduce scrap on the line. So this is not just predicting defects on the line, but it's actually being prescriptive and making recommendations on what is the best offset parameters. My recipe that's running the line, right? What's the best recipe parameters? And in some cases, we have clients that are feeding those recipe parameters back to the line, to the PLC, automatically, okay? So the line is always running in a balanced way with the best recipe settings and with the most optimized quality checks, all right? So again, it's a maturity scale, right? We start with data collection, we go into predictive quality, and then we go into prescriptive decision-making or prescriptive quality. This is just an example. Some of the information that is being accessed. The rib height is key, so you're able to monitor the rib height over time, and you're able to view that. And it is a multivariate system, of course, but you can go deeper and you can look at each variable and the impact of the rib height to the deviations of the variable. Okay, but more importantly, you see a heat map. If I'm the quality engineer, right, quality manager of this line, I see a heat map and I'm able to diagnose the relationship between the process parameter and the predicted quality or defect on the line. All the reds here are actually defective oven doors that have been rejected on the line. In real time, the solution has made a decision to reject them. And then we are visualizing this in a type of user-friendly mode to the quality manager, so they understand the temperature zones right here, where there is usually an issue with the oven door, right? Like a temperature of less than 120 degrees usually has quality issues on the oven, right? For those who might be interested, actually, we were able to hit almost an 88-90% prediction precision accuracy on this application, which actually exceeded significantly the previous quality rates or quality accuracies that were in place prior to this system being in place. But at the end of the day, to make the system work, right, we need specific data map that makes sense. We need correlation to the quality labels and quality parameters on the line. And we need that business case that we're trying to solve, which is, hey, I have an issue on the specific oven type, and there are warranty and recall issues. How can I immediately tackle that problem and use advanced analytics? Another example is from the automotive industry. Similar use case. If you're interested in the slides, just please email me at the end and I'm happy to share them with you. But the motivation here is a little bit different, okay? And I can talk to it. These guys are making aluminum wheels. If you look at your car, your tires, you got 4 tires, that the hubs and the rims right in the middle are actually produced by this automotive tier supplier. And nowadays it's mostly aluminum, right? Because of the light weighting of the vehicles. Low pressure casting is a key application in this industry, okay? And in a low pressure casting machine, you're talking about 30 to 40 key process parameters. And there's a robot that picks up the part and then lets it go to the machining and takes it first to the X-ray. But due to the volume of the wheels, right? I'm making a wheel every 15 seconds. I cannot inspect every wheel. There's an X-ray machine that inspects, but the inspection time is long, and I have to inspect in a more selective manner, right? So they started making a lot of scrap, more than normal actually. And we implemented a predictive quality solution that took historical data from the X-ray, which is kind of pass-fail, and the casting parameters. And we implemented a model, a predictive quality model that could easily display and auto-reject wheels that are non-conforming, okay? And if you see here, imagine you're running this casting cell and you're seeing this in real time. Green is actually a acceptable wheel. It's a good part. Yellow is a warning or a suspect wheel that could be bad because the accuracy, you know, of the model didn't show confidence. And then red is a high prediction of a quality issue. So it is visual. You can remove the wheels manually from the line and auto reject them, or in this case, the robot is actually automated to auto reject the wheels. But the more important thing here is actually the diagnosis. Okay, if I take my mouse and hover over this red one, the reason that this wheel was rejected is the temperature of thermocouple number 1 on the cell and the pressure cooling flow number 6, right? Where the two parameters from this multivariate analysis that is running every 15 seconds on the line, a wheel every 15 seconds, but those two parameters are actually the contributing factors to this specific reject. So now that the client knows the reason for those rejects, there is reporting capability, and the client can go deeper into the software to understand, why do I keep getting bad wheels that are related to the temperature of thermocouple 1, or the pressure cooling flow 6. And then there is some PDCA, plan, do, check, act, countermeasure activity that the quality team can do to start making reductions in those wheels. So if such a system is not in place, some of those wheels may go to the X-ray, but some may not go to the X-ray actually, and they may end up slipping to the next process, and they don't get caught until final inspection after they're machined and after they're painted, right? And now it's extremely costly to rework those parts back into the system, right? So how do I improve velocity, right? I want to make more parts, but I also want to make more good parts that are shipped to the client in a timely fashion. This is just an example of the root cause analysis behind it. Most important thing is, the prediction accuracy is about 96%, okay? About 4 weeks of training data is required for a good wheel and for different scrap type wheels, right? But once that training data is accumulated and the models are trained and validated, usually those type of solutions could achieve about a 95% plus prediction accuracy. Again, very applicable to many industries. Again, this is automotive, but I showed CPG, semiconductor industry. Think about some of those applications for your industry, for the folks on the call. Last case study, and if you have questions, just please drop them in and we'll come back to them. But high pressure die casting is key in the automotive industry, and this is a good concluding case study because it goes back to our early conversation about business case. Business case drives everything, especially in these industries where the margins are extremely slim. Automotive industry margins are extremely sensitive. And if I'm catching quality issues in the foundry, okay, the cost to rework, maybe remelt the part is about $3.8. Okay, but look at how it jumps, right? If I catch the quality issue in machining, if I catch it in the assembly area afterwards when I'm doing painting and assembly, and if it goes to the customer, not to mention the warranty recall claims that may potentially come out of this. So it's important to understand your costs per part and per scrap part across the value stream, and to be able to put such solutions in place right at the source of quality issues, which is usually the foundry, okay? And if they're caught in the foundry, you're able to completely minimize quality issues across the rest of your value stream. Early scrap detection, as we call it, right? Early scrap detection and prediction early in the value stream can easily provide in the casting industry, as I had mentioned before, about a $250,000 savings per annum per plant. Okay, so keeping the business case in mind, this is a bit more of an advanced case study. There's a lot more moving parts. Okay, there's about 50 casting parameters for every shot that I had mentioned briefly earlier, right? Every 6 seconds, there's an aluminum cast shot into the cavity. and there's 50 parameters collected from the PLC, okay? Some of the key parameters are actually listed here. The pressures, the airflows, the temperatures, the oil levels. Some of the data, by the way, can be used for predictive maintenance of some of the key assets here, like the trim press, the die, the dosing furnace. But the parameters exhibit different thresholds for different product IDs that run on the machine. And by implementing AI and a multivariate analysis of those 50 parameters, we're able, with a high level of accuracy, to correlate them to the part quality and make prescriptive decisions on the machine. So the outcome of the project was actually, both a predictive and prescriptive quality application, where within every 6 seconds there's an auto part segregation. Okay. So, right here, if you notice, these are kind of all the variables or the top variables that are being collected. And if any variable is a red, this part is rejected, okay? And if multiple variables are yellow, the part is also rejected. So there's specific rules, right, based on the AI that is running and the learning that allows us to, reject this part here, which is running on cell 1, and let this part pass, which is running on cell 2. But the science of making this happen is, again, having the right data synchronized and labeled, connectivity to that PLC, right? And training the models with the right data for each type of good part and each scrap part. So the training of the models when it comes to PDQ is a bit more intense. But once it is done once, it actually would run for a lifetime, and it would deliver value to the business. So this is a mission critical solution, actually. Quality 4.0, unlike predictive maintenance, Quality 4.0 is mission critical. It's actively predicting, actively prescribing action within seconds. It's an online solution. With predictive maintenance, it might take time for my machine to fail. It might take a day, it might take a week or a month, right? But with Quality 4.0, I am making decisions for every product that is being produced on that machine. So a short summary, and I hope this was useful for the audience here. I want to start with this. I love this. If you have not seen this, LNS Research in 2017 published Quality 4.0 Impact. Okay. If you reach out to me for the presentation, I can also send this to you. You may have seen this. It might look busy, but I love one sentence here. There's one key sentence. Manufacturers looking to improve quality should assess where they stand on each of these 11 axes, okay? It is likely that many companies will need to make investments first in traditional quality before they can leverage Quality 4.0. I 100% agree, okay? Every manufacturer has a different level of digital maturity or quality maturity. You cannot just, go in without even having a proper quality procedure. I don't even use an SPC system in my shop, but I'm gonna go put predictive quality on my casting machine. Sorry, it's a recipe for failure, unfortunately. There are fundamental quality things that through ASQ and so on and so forth that must be in place to be successful going beyond and using AI and implementing Quality 4.0 solutions. So I think that's a very important point to make. Foundation is key for success in predictive quality or Quality 4.0. But there's also a way to be successful, right? And I'll keep this brief, but there is an assessment phase. I need to understand my baseline. I need to understand my maturity level, right? There are workshops that look at gaps, my people, my process, my technology. What's my maturity level? It's good to think big, but we have to start small. We have to find a proof of value, okay? It's not a proof of concept. This is a proof of value with a business case, a business ROI justification, and a technology that makes sense for your business. And business plus technology, when implemented, deliver value for your business. This is a proof of value. And this should not run for 6 months to 1 year. This should run for about 2 to 3 months, okay? It's very focused, success criteria, people, process, technology will make you successful. And then you learn and scale those solutions. And those solutions you could potentially learn and scale internally within your organization, right? So find your proof of value, assess your maturity, and make sure you have the foundations for quality 4.0, which is traditional quality, right? That allows you to then go beyond and embark on using advanced analytics and predictive quality solutions to detect, diagnose, and predict deviations in your critical assets, right? So I hope today was useful for everybody. Please reach out to me. My email is simple, abuali@iotco.com, ABUALI. If you're in front of a computer now, just type me an email, say send presentation, I'll send it to you, and link with me, and let's stay connected. And I think I'm on time, Manny. We got 15 minutes for questions, sir.
Yes, Mo, you're doing very nicely. So I would encourage folks to do a couple things. One is I put out my email address in the chat. So if you've got any questions or concerns about the webinar, you need some information, you can contact me directly. Mo is showing his email address. Thank you for that. Mo, I got to tell you, this was a pretty cool presentation. Easy to understand for someone who doesn't know an awful lot about the topic. And I feel like, yeah, I could be successful with it. We do have some questions. I would encourage some more questions, please. And we will answer all the ones that we can in the time available. So anything else you want to say before we get into questions, Mo, or shall we get started? Okay, let's do that then. So somebody asked if there were any examples or case studies from the elevator and escalator industry. To me, that just, I don't know if it's industry specific so much as it is process specific, though. I mean, any thoughts?
Yeah, that's a good question. We have done work in the elevator industry. To be honest, it's more related to predictive maintenance of the elevator door and the elevator, shaft and so on. It's obviously a safety critical piece of equipment, but I would say quality here is a bit of a different flavor. It's more of predicting, the energy usage actually of the elevator. So it's not the quality of the part. The impact is usually the energy used by the elevator. So different flavor here, but same approach actually, same systematic approach. But the connectivity, the data map, and the energy side of it, I would say, is more applicable than quality.
Well, I think there you're talking about the elevator in use versus the elevator being manufactured. I mean, everything you talked about still applies to manufacturing. So, okay.
Yeah.
Another question: are trends and shifts identified using predictive quality?
Yeah, they surely are.
Okay.
I think the diagnosis component or the root cause analysis of the PDQ is important. I mean, these models are showing you predictions that you're going to make a good or a bad part, but there has to be a reason behind, the model accepting or rejecting, right? So you would see trends from the data, and you would see trends also from the features, which are the metrics and the statistics of the data. And those trends would typically tell you, more insights. Like the example of the casting company I talked about, they realize they're rejecting a lot of wheels because the temperature on a specific thermocouple, like thermocouple number 1, was always giving them a problem. So that helped them with the root cause investigation, and then it turned out that there is some issues on the machine that they were able to investigate based on that. So yes, trends and shifts are definitely identified, and you have to act based on the information.
Got it. Okay, I've got a comment and 2 questions. Comment was great presentation and examples that bring clarity to the topic. First question: does every application of the AI require a unique programming effort, or has programming grown to a place where checkboxes allow you to a la carte the program to serve the intent?
Yeah, and I can see the question actually. It's a good question. I mean, we've moved into a more template-based approach of doing things. Initially you do have to configure and train models and so on and so forth. There are tools out there today that allow you to configure that recipe without any programming. Actually, it's what I call a no-code environment. So those templates do allow for a no-code environment. Yeah, reach out to me. Happy to offer you more information.
And then second question from this person: does the AI function allow us to improve the manufacturing process so that scrap continues to be reduced?
That is the goal. And the best way to do this is to start to be prescriptive, actually, and to take the human out of the loop and start feeding data back directly to the process to offset the recipes and improve the line performance. So that's the natural maturity or extension of these models to become more prescriptive. So in this case, you would surely continue, having scrap reductions and optimizations on the line.
And I guess as you continue to refine your model and really get to the edges of the data, what's good, what's bad, it gets better in a predictive fashion, more information you have, right? Okay. Comment, amazing how the technology has evolved to enable significant quality improvements.
I would say, Manny, it's also amazing how a lot of people are not adopting it.
Well, not invented here. I mean, there's all sorts of reasons, right? So
what I just said today, guys, in the last 60 minutes is things that have been happening over the last 20 years, 20. But now it is fueled by improving in computation speed, reduction in the cost of storage, cloud, networking. So, hey, if you're not adopting this today, start adopting it now because your competitor is.
So I suspect I know the answer to this question too. It's much like savings, but the question is, when is the best time to implement, especially in a startup? Would you do a first thing, or would you stabilize your process and then implement, or what would you do?
It's a good question. I think it goes to my conclusion there, where there are some fundamentals that you have to have in place. There is traditional quality tools that ASQ delivers very well. Anywhere from your process, your people being trained, the use of connectivity, the use of SPC tools. Those fundamentals need to be in place, and then it would allow you to go beyond into the predictive quality realm.
Okay. Another question, examples for the medical device industry. Are there any?
Many. A lot of CNC machines, a lot of EDM machines making good medical parts with very precision parts. I would say a lot of the applications around CNC machine, predictive quality, a little bit of robotic predictive quality, injection molding predictive quality. I did not touch upon them today. Please reach out to me. But a lot of templates available for the med device industry.
I know, there's never enough time to cover everything, right?
And they're very mature. What I love about med device is that they're very mature about the data acquisition and the connectivity in many cases because they're heavily regulated.
Yeah, they definitely have to show lots of things. Here's a question. How could this be applied to transactional processes, let's say maybe in banking or possibly healthcare?
I'm sure it can, but Ron, I'm a manufacturing guy. I got oil in my blood, so I would not be able to answer your question, man.
Okay, could be interesting extension of the technology. Another one, obviously, does PDQ apply to a final assembly operation where the vast majority of parts are purchased from various suppliers?
That could be possible, and I give you a small example. Think about image data. There is a lot of image analytics for the final end-of-line assembly that are taking pictures of parts, and we're doing predictive quality on the image data. I think that's a very wise application and the use of sensor technology in the final assembly area.
Okay. Yeah, I guess also you could use sensors of various types to see if something is inserted fully or whatnot. So,
correct.
Another one about the assessment, is there a guideline or can you give an example about how to assess the actual process and the needed information to obtain?
Yeah, it was actually in the beginning of my presentation. We would need to look at material type of data, process type of data, quality inspection type of data. So there is a defined data map, which I think was in a beginning slide that I had shown. Happy to discuss that with you further. But in many cases, you have the data map, but the issue is it is not synchronized together. You got system A, system B, system C, and the labels are not synchronized. So there is a bit of a data preparation synchronization work that happens in the beginning to make sure that the proper data goes into the models. That's kind of the challenge there.
Okay, we've got a couple of questions about costs, talking about ROI or the startup cost. Can you talk a little bit about that perhaps?
A mid-sized casting plant saves $250K per plant per year by just improving scrap by 1%. and the cost of the software and the infrastructure and the services combined is less than 250K. So that's your ROI.
So you're saying less than a year? I mean, months, maybe,
Less
depending
than a
on
year.
your
Absolutely
cost.
less than a year. I would say predictive quality ROI is even much more tangible than predictive maintenance ROI. You could give a hard quantification. So the ROI justifications of PDQ are very much in line with the 6 to 12 month ROI within manufacturers. And we have sample ROI calculations I can share. If you reach out to me and tell me your industry type, I can give you some examples.
Okay, I have a couple of questions related to case studies or application for autonomous robotics space.
I think Elizabeth, sorry, re-asked at the bottom, what is the cost of the tech? The cost of the tech is in a mid-sized plant is usually under somewhere between 100 to 200K. But that includes the software, the services, and the training, and the internal infrastructure of the client. And the ROI is usually within less than 12 months.
Okay.
And I'm sorry, going back to your question again, Manny?
About case studies or use cases for autonomous robotic space.
We have done some work in the cobots realm, the collaborative robots area. We've done work in the traditional industrial robots, where we've looked at the spot welding quality, the laser welding quality, friction welding quality. So basically, when the robot moves and it degrades, sometimes it impacts the quality of the weld or the quality of the material handling. So that is a predictive quality application. I hope that helps. I'm not sure what autonomous means, but that's an example of a robotic application.
No, I think you hit it pretty well. Folks, we have some time for some more questions. I have one. Mo, can you tell us a little bit about what volume of production might be viable in this case? I mean, I can see where you're doing high volume, heavy automation, but a lot of my clients don't look like that.
Yeah, it's a good question. We do definitely see high volume manufacturers as a key participant in this type of technology, but more and more aerospace and defense providers where they're making precision machine parts, very long cycle times, they're making one-offs, but there is an impact of the machining parameters to the surface roughness or the surface texture of the part that they're aerospacing on a CNC machine, for example. So definitely an application in the high mix, low volume industry where you need precision and the parts are going to a safety critical type of industry, like on a jet airplane. There's definitely an application there.
Okay, gotcha. So I have another question here. It's any comments or tips on winning over folks on the floor and that are directly managing the processes where many are historically reacting or operating in a more reactionary mode, and the business case itself may not be a selling point?
Yeah, we actually just released an article I can share with you about the people side of things. It's kind of, I think it's called 5 Tips, to involve people in digital manufacturing, and I can share that article with you. But I think, long story short, fostering a culture of innovation, having a multidisciplinary team, setting up a steering digital committee, right? Especially in the larger organization, there needs to be a corporate and plant level representatives that talk to each other. There must be a feeling of empowerment, right? And the feeling of solutions being shoved down by corporate is usually not well taken. It doesn't become successful. So I have 5 or 6 tips I can share with you that we've published in an article this month. But again, it's a multidisciplinary approach. And I would tell you, people, process, technology, you'll only be as successful as the weak link or the weakest link. And in most cases, unfortunately, technology is not successful because people are not involved or trained or empowered in the right way within the project.
All right, I think we've got time for one more question. So somebody works in a sheet metal facility with press brakes. So they use the same tools to make lots of different parts. They have over 1,000 parts available. Can it be utilized on the tooling itself or and it's small runs? So I guess it relates back to my previous question.
Yeah, we can look at the process. I mean, right now we're doing a brake press project with an industrial manufacturer called Train Technologies, Ingersoll Rand, and the large press brakes. But the key issue is actually uptime because it's a high volume machine, and uptime is an issue, right? You're losing parts. So we're doing predictive maintenance on the key critical components of the press brake. We have not looked into predictive quality yet on that machine. But to be honest, I would have to talk to you a bit more and do a discovery to understand how we can correlate this to quality. I unfortunately can't think of anything off the top of my mind today. Yeah.
Sure, it can be tough, and honestly, I mean, we get questions that are 10 words or so. It's hard to know sometimes what the intent of the question is.
Yeah, it is a
All
good
right,
question though.
folks.
I'm happy to explore it further. Yeah.
Yeah, absolutely. Folks, I can tell you again, after having worked with and talked to Mo for months, he's very approachable. Even though he has a PhD, his head's not in the clouds. Feel free to reach out and talk to him. I think he would welcome the connections, not to mention just that's being him. So it's the top of the hour, folks. We are going to shut off this particular webinar. Thank you again, Mo. We've gotten several thanks, several great presentations. I would echo that. As a reminder, you're going to get your RU certificates, should occur automatically within 24 hours. If not, feel free to email me directly. My email is in the chat. And we'll be posting the video by Friday, most likely by tomorrow. So, thank you again. If you want to hang on for a little bit, then we'll let everybody else go about the rest of their day. Thank you for your time and attention. It's much appreciated. Have a great day,
Thank you for
folks.
the opportunity, man, and the team. And many